In this final video of the first three parts dealing with water, acids, and bases, we're finally going to see why we care about weak acids and weak bases. And here's the reason why, is because the majority of biochemical reactions are done in what's known as buffers. So what buffers are they resist changes in pH when small amounts of protons or hydroxide ions are added. And so what happens is these are in equilibrium. So you have the weak acid and its conjugate base, or you have the weak base and its conjugate acid. So what happens is, if in the solution we add acid, it's going to drive the equilibrium to make more conjugate acid. If we add base, it's going to drive it the other way. And so what buffers do is they resist these changes in pH. And that's very important because a lot of our proteins and enzymes and the things that we're going to talk about are very particular about a specific pH. And so what happens is, for a buffer, if we look at a curve, a titration curve, so this is going to be the amount of OH added, and this is going to be the pH. What we see is that for a buffer is a curve that kind of resembles this, something similar to that. And what we know is this flat region is known as the buffering region, or the buffer zone. This is the region where the buffer is at its most effective at a buffering region. And what we find out, and I will show you why this is the case, usually when the pH is equal to the pKa of your weak acid, that will be the perfect buffer. That will be the perfect buffer. So let's go ahead and let's look at an example of this. So we have acetic acid. I'm going to draw it like this. Plus, we have sodium acetate, which is its conjugate base. So acetic acid, sodium acetate. We find that this is the strongest buffer when the concentration is 50-50. When it's 50-50. And so the pKa is 4.8 for acetic acid. So we know at 4.8, when the pH is equal to 4.8, we are at our maximum buffering capacity, which is great. We also have a region of buffering, which is +1 or -1 of your pKa. So we know that the region that this is a very good buffer is between pH of 3.8 and a pH of 5.8. So how in the world do we know this? How in the world do we know that 50-50 is the best, that's when the buffering is great? So we're going to go back to our equation. I know, more equations. And what we're going to do is this. So we have Ka. So we're going to look at our Ka equation. And what we're going to do is this. I'm going to drop H3O plus out of the numerator and just put it out in front. That means the same thing. So this, circle it in a different, let's do purple. Go crew. This is the same as that, right? So what we're going to do is we're going to take the negative logs of everything. And so what we're going to do is we're going to have, let me go back to red. Negative log of Ka is going to equal negative log H3O plus minus log of A minus over HA. Okay? So we've seen some of these terms before. What is negative log of Ka? I'm going to draw this new equation over here. So what is the negative log of Ka? I'll give you guys 2 seconds to answer that. If you said pKa You are correct. Now, what is negative log of H3O plus? pH is correct. And then we get minus log of A minus over HA. And since I don't like using negatives, there's a negative, I'm going to move this group over to the other side. And so what we're going to get, I'm going to do this on a new slide, is pH is equal to pKa plus the log of A minus, which is the amount of conjugate base, or weak base, times HA, which is the amount of weak acid or conjugate acid. So let's go back to the question I asked before. Why is 50-50 the best region of this buffer? Why is pH equals pKa when this buffer is the best? Let's look at this ratio right here. We said 50-50. When we divide 50 by 50, what do we get? We get 1. When you take the log of 1 is 0. So I'm just going to cross that out. pH is equal to pKa when the weak acid and the weak base are 50-50. And so why do we care? Right? Who cares? Great, this is buffers. I have another video on the channel that I would recommend you looking at on how we can use Henderson-Hasselbalch to do a variety of different buffering calculations. That video will go in more depth into actually how we can use this equation. But what we can use is we can look at titration curves for amino acids. So we're going to talk about amino acids later. Every amino acid in our body has buffering capacity. Just depending on which amino acid determines where it is. And so we're going to look at one. Kind of extended it a little bit. So here's a pKa at about 3.05. Here's a pKa at about 6.15. And here's one at about 9.25. It'll go up after that. And so this is the titration curve of histidine. And so what does histidine look like? Histidine looks like this. We'll come back to the drawing, or to the titration curve. And so what we see, this is in its fully protonated form. Histidine is a very important amino acid. And so what we can see here, all of these protons, this proton, that proton, all have pKa values. They can all be removed. And depending on, so here's 3, here's about 6, and here's about 9. This proton is very, very important in biological functions, not important for this purpose. But what we can see is around every pKa that we hit, where we lose those protons, is where we get our buffer. And so this is why we care about buffers. This is why we care about using titration curves. This is why we care about what we're doing now. So hopefully you enjoyed these first 3 videos. This will transition. In the next set of videos, we'll start talking about amino acids, what they are, how they're used, and start talking a little bit about protein folding as well.